Hi guys, this is AQA GCSE Science, and today we're looking at chemistry, more specifically quantitative chemistry. And really, it sounds quite fancy, but it's not that big. Quantitative just means it's all about amount, how much of something you have. And there's quite a few topics in here. Some of them foundation, some of them higher. So if I say higher, I will say that it's higher, higher tier. This is all for the combined science exams, and we'll start with conservation of mass. Conservation of mass is relatively simple. You take a chemical reaction, let's say hydrochloric acid, HCl, plus sodium hydroxide, makes water and sodium chloride. Now, I'm sure a lot of you can recognise here, this is a neutralisation reaction. So we have our acid, we have our alkali, and it produces water and a salt. But what the conservation of mass means is that all of the mass that we have in the first part, in the reactant, is equal to all of the mass in the products. So we've got mass here, and a big equal sign. They're equal, yeah? So that means that however many atoms we have on the left, we have the same amount of atoms on the right. And that means that we don't just magically create atoms or magically destroy atoms. You cannot create nor destroy the atoms. They're just there. And you can change them around, so you can change it so that the hydrogen is with the oxygen now. But it doesn't mean that you're just making atoms and creating atoms. So another way of putting it is either mass of product or reactants equals mass of reactants. Simple. So we do not just make or destroy atoms or mass. Okay? So that's the very first bit that we have of quantitative chemistry. The next bit we've got to understand is about relative formula mass and relative atomic mass. So, you might have heard of relative atomic mass, and I hope you have, but if you can get up a periodic table, if you want to Google and just Google up GCSE AQA periodic table, and it will come up, and all of a sudden you will be presented with a periodic table. Hopefully you've seen one before. It's got a lot of different squares on it, and I'll give you 3 examples that are really important because we're just dealing with sodium hydroxide. Sodium hydroxide has sodium, oxygen and hydrogen in it, and we get up our periodic table, and on our periodic table we have all of our different elements. So you're going to go and you're going to find each of the boxes, and there will be a box that says Na, there'll be a box that says O, and a box that says H. It'll say the name underneath, so sodium, oxygen, hydrogen. It won't actually have a scribble. It will tell you exactly what it is, and it will give you a big number on the top. So for sodium that's 23, and a small number on the bottom, which is 11. Oxygen has a big number of 16 at the top, small number of 8 at the bottom. Hydrogen has the big number of 1 and the small number of 1, so it's both 1. And hopefully you've looked at this already, but the bottom number here is the proton number. That's the number of protons we have in our nucleus. Now remember, our nucleus is made up of lots of different protons and lots of different neutrons. Protons are positive, neutrons are neutral, and we've got our electrons whizzing around the outside. These are all negative. Yeah. So this here, this 11 tells us that we have 11 protons in our nucleus. In our nucleus. However, this 23 is the mass number, the RAM, or relative atomic mass number. And that means it's the total number of protons and neutrons added together. So, if we do 23 take 11, that gets you to 12. And therefore, there are 12 neutrons in the nucleus. Hopefully you know this. But the important thing to note is the big number, this one here, is the relative atomic mass number. Now, you can add relative atomic masses together. So if we take RAM of sodium, so that's just sodium's RAM, and you add RAM of oxygen, add RAM of hydrogen, we get something called the RFM, the relative formula mass, and that's of sodium hydroxide. So, to calculate this relative formula mass, the mass of this, we add this big number, add this big number, add this big number. 23, oh, wrong colour, 23, add 16, add 1, gets out to 40. So the relative formula mass is 40. Another way of looking at it is that it is the total number of protons and neutrons in this whole compound here. So that is another thing that you need to know. These are both foundation. So that is an important thing to know. If you're doing higher, you really should know that. But foundation's where it's at there. Quantitative chemistry, mass changes. Right. The next thing is talking about when a reactant or a product is a gas. And it's still talking about back to the conservation of mass. Mass cannot be created or destroyed, so you can't magically create atoms or destroy atoms. So, what if we took metal plus acid is salt plus hydrogen, right? We all know that, MASH. So, let's take ourselves sodium. One moment. Yeah. So sodium plus hydrochloric acid go create sodium chloride plus hydrogen. So we balance this. It's not so important at the moment. 2, 2, 2, is that right? Yes, so we balance this and we know that the mass of the start bit is equal to the mass of the second bit. Conservation of mass. But it might not appear that way, and it could ask you why. So the way we actually do this is we take a conical flask, excuse my horrible drawing, and we pour in some hydrochloric acid. So, hydrochloric acid. Then we take our sodium, and this is like a little block, and that's our sodium. Put our sodium in, and our sodium slowly dissolves, reacts even, and it appears to melt. Now, if we weighed this before and after, remember taking away the mass of the conical flask, because the conical flask weighs something. So if we weigh it, we weigh the conical flask originally, CF, and that's say 25 grams, and then we put in the metals, so CF with metal, there we go, say it's 27 grams. The metal is now, this is metal and acid, so it's now 27, take 25, so it's 2 grams. So the sodium and the hydrochloric acid added together is 2 grams total. But, say if we waited for the reaction to finish, and we expected there to be 2 grams still left in, and we weigh it, and all of a sudden we get 1 gram. Where has that other gram gone? Now, we need to remember that we've got a solid, liquid, and then a gas. Hydrogen's a gas. Hydrogen's a gas. So where's the gas going to go? The gas is just going to escape. So, we need to know that there might be an error because the gas has escaped. And to fix that, we put on something called a bung, which is basically just a big stopper. B-U-N-G, bung. We put on a big stopper, and that stops any gas from coming out. Okay? And therefore, the mass could be the same. We also need to know that how we can measure our gas. And there are 2 main ways of doing that. The main way, using something called a gas syringe. So if we want to measure the hydrogen given off of this, ignore our bung's gone now, we could use something called a gas syringe, which is basically just a big cylinder, and it's got a pump in it, and basically however much gas comes out, it pushes the pump further and further back that way until a number's read up here. These are numbers, and so you can read it, and that's the gas syringe. That's how you measure it. Then another way of doing it is by taking a tray of water, there's water in here, an upturned measuring cylinder, pipe it in underneath, and up through there, and this is all full of water, so it bubbles at the top, and it creates that looks like a little smiley face, and it creates a line. So on the actual conical flask, you've got water up to this point, and at this point there's the gas, and it's got measurements, so you check at that point where the gas is, and that's how you can measure some of the gas. So, important thing to remember, when a product is a gas, it can escape, and you need to be wary that the mass may appear to change, but it never does. Go on. The next thing you guys have got to know is the uncertainty. And the uncertainty is basically how much a result can differ. So we've got a temperature reading, okay? We've got 12 degrees Celsius, 12.2 degrees Celsius, 12.3 degrees Celsius, and we've got 15 degrees Celsius. So, 1, 2, 3, 4. First, the question asks you, find the average. Now, you can give this a go yourself if you want, but it is excluding the anomaly. Find the mean, or in other words, the average. So, I'll give you a moment to have a look at that if you want. And in 3, 2, 1. Great, let's give it a go. First of all, we need to understand what is an anomaly. So an anomaly is basically a result that doesn't fit with the other results. So, what numbers are close together? 12, 12.2, and 12.3. They're all very, very close together. But we have 15. 15 is really far off of 12 compared to 12.2 and 12.3. So, that is our anomaly. It doesn't make sense. So, we can already just disregard that. So, excluding the anomaly, And we've got a big tick already for doing that. Find the mean. Now the mean, we just add up 12, add 12.2, add 12.3, divided by 3. Simple. Because we have 3 different values and you add them together. That's how you find the mean. 12 at 12. And that gets you out to 12.167. So let's do 12.17 then. Great, that's the mean. That's the mean. But we found that. But now the big thing, the new thing that we've got to do is find the degree of uncertainty. So find the uncertainty. Now this is average, so it's not 100% accurate. So the uncertainty is really just a measure of how accurate or not the actual result, if I put my unit in, is. So we do that by taking our original values, we take the largest value, and we subtract from it the biggest value. So we've got 12.3, take 12 is 0.3. 0.3 divided by 2, 0.15. Boom! So, we do a very fancy symbol. We do 12.17 degrees Celsius is our mean, plus minus, so that is literally just a plus on top of a minus, are 0.15 degrees Celsius. And that is the answer. And that could be 4 marks. We have excluded the anomaly. We have found the mean. Here's how we found the mean. We have found the uncertainty. And we have used our units. And units are really important. And we formatted it in the right way as well. That's all the foundation stuff. But if you're doing higher, remember, you've got to know this as well. It's really quite important. The next bit is about moles. What moles are, and this is a tricky concept to understand. The way I like to teach it is moles are an amount. Okay? It's like another way of saying I have a certain amount of something. I have 5 sweets. You have 12 sweets. I have a pack of chocolates. You don't have a pack of chocolates. It's how much of something you have. And remember, quantitative means how much of something do we have? And that's the really important bit. So, starting with moles. It is about amount. Mole. It's not like the little creature that burrows underground, no. M-O-L-E-S. And the unit is the mole. M-O-L. Right, so if I have 5 moles, I have 5 of a certain amount of a chemical. Now remember, this is higher tier only, so that's really important to understand. That's SHT. So, I have a certain amount of a chemical. So, let's say I have sodium hydroxide. Okay? What if I say I have 5 moles of sodium hydroxide? What does that mean? Well, as I said, a mole is just a big way of measuring something. A mole is just a way of saying I have a certain number of atoms of this. 1 mole is equal to 6.02 times 10 to the power of 23 atoms. And if you just put that in your calculator and you get rid of that and you just keep multiplying, it is a massive number. So that's a lot of atoms in 1 mole. Okay? And so 1 mole is really just a shorthand, a short way of saying I have 6.02 times 10 to the 23rd atoms. And this is called the Avogadro constant. And it's named after a guy called Avogadro. And you guys should know this because it's unlikely that you'll be given to it. Because in chemistry you're not given formula sheets. Until 2027 you'll get formula sheets for physics and for maths, but not for biology and chemistry. So, let's understand what 5 moles of sodium hydroxide would be. Well, if we know 1 mole is 6.02 times 10 to the 23rd atoms, we know that we can multiply by 5 to get from 1 mole to 5 moles. So, we do the same. We multiply by 5 of that 6.02 times 10 to the 23. And we get 3.01 times 10 to the 23, times 10 to the 24 atoms to the power of 24. Let's make this neater so you can read it. So times 10 to the power of 24 atoms. And it's that simple. This is how many atoms that you have. And that's quite an important concept. It's just another way of saying I have a lot of atoms. Specifically, this many atoms, or this many atoms. In 5 moles of sodium hydroxide, I have this many atoms. And it's basically just a really long way of saying that. Now, another thing to note, and don't worry about this at the moment, that's just for later, but another thing to note is that there is an equation that goes with moles. We have mass, moles, and MR. I hope a lot of you can get versed with this one quickly because it's quite important. All that means is that we can convert between mass in grams, MR doesn't have a unit, or that could be relative atomic mass. I've looked at it as RAM before, or RFM, and moles. Now, another way of writing RAM is MR, and that is AR for the. Now, another way of writing RAM is AR. Another way of writing RFM is MR, and that's simply how it is. So, and moles, of course, have the unit mole, MOL. So you can use this to calculate equations. So, we're going to use that in a minute. It's going to be really, really important, okay? I'll give you one example, okay? We'll have a look at it. Sodium. And let's say 8 moles. What mass? Boom. And I'll give you can pause the video and give it a go. I'll give you 5, 4, 3, 2, 1, boom. Okay, sodium. We look at sodium on our periodic table. Sodium has the big number at the top of 23. So that's its MR. And it has 8 moles, so we have to do multiply by 2. Now, mass is no longer in the equation, so we cover up mass. We've got moles times MR. So we do 23 times our 8 moles, and 23 times 8 is 184. And so we have our mass of 184 grams. So 8 moles of sodium, there are 184 grams. And we'll use that equation in just one moment. So, we've got our chemical reaction, and I spoke about this earlier. We've got our sodium hydroxide, our hydrochloric acid, our sodium going to sodium chloride and water. Neutralization reaction, NaOH, HCl, NaCl, and H2O. So, we're going to look at these, and we're going to split them up. We are going to create a little table, and we'll start with the MR, or AR, so that's the relative atomic mass, MR there. I'll just try and move this back a tiny bit. So MR, so that's one thing. Then we've got our ratio. That's ratio. And I really do encourage you to write out all of these tables when you go and do it. So yes, that's your ratio. Then we have our MR ratio mass, and we have our moles, and that's it. So, boom, boom, and we can just start working things out from there. And we're going to work everything out, but it might ask you just to find a single chemical, or the mass of a single chemical, or the moles of a single chemical. And we're just going to use all of the knowledge we have to try and figure that out. Okay? I'm going to start and say that we have 11 grams of sodium hydroxide. So, our mass is 11 grams. Okay? And we're going to fill out the rest of the table just from that information. So we can start. Sodium hydroxide, we look at the MR. And that is 40, as we looked at earlier, didn't we? So we have 40, and that's because that's 23 and 16 and 1. HCl's MR is 36.5 because it's 35.5 plus, hold on, let me write this in the right colour, because it's 35.5 plus 1, 35.5 for the chlorine and 1 for the hydrogen, 36.5. Then we have our sodium chloride, we have 23 plus 35.5. So 23, 35.5, 58.5. And the last one I just know off by heart is 18. But you can calculate it out yourself. You have 1 plus 1 plus 16. So we've got all our MRs. So we've already filled out a row. We've already filled out, what, a quarter of all the values we need. Just over a quarter of all the values we need. And now we'll look at the ratio. The ratio is the whole numbers that are out the side. So we've got no big numbers in this symbol equation. So that means that they're all just one. There's a hidden one here. There's a hidden one here, a hidden one here, and a hidden one here. So the ratio is simply 1 to 1 to 1 to 1 to 1. Okay? And we'll look at an example in a minute at what happens when it's not 1 to 1 to 1 to 1 to 1. And that will become important in a moment. And then we need to use our equation to find out moles from our MR and our mass. Because this is the only one we can figure out moles for. So we figure out moles here. So mass goes at the top, moles, and then we have our MR. What do we want to find? We want to find our moles. So we cover up our moles. That means we do mass divided by MR. So it's that divided by that. So mass over MR is equal to 11 over 40. And I want that into a decimal because I'm a scientist and I'm not a mathematician. 0.275. So we have 0.275 moles. And because the ratio is 1, that means we're going to have 0.275 moles of everything. I will give you an example later when that's not the case. First of all, we'll start with 0.275 moles. Remember our unit? MOL. Perfect. Everyone got that? Good. Now we've got everything we need just to find the mass. And to find the mass, we're going to do, we're going to write out our equation. Mass, mole, MR. Now, hopefully by the end of this will be ingrained in your memory. But we've got to find mass, so here, that means we'll do moles times. Ooh, you guys falling over. And that means we'll do moles multiplied by MR. And that means, if I can put this out without getting rid of my units, that we must do our 36.5 times 0.275. 275, what am I doing? I'm not neat today. 36.5 times 0.275, and that gets you to 10.03, or let's just do 10.0, so it's just going to be 10. I'm going to round to one decimal place, so that's 10 grams. Then we've got to do 58.5 times 0.275. And that gets you out to 16.087. 16.087 rounds up to 16.1 grams. And for the last one, we've got to do 18 multiplied by 0.275. Put that into a calculator and you get out 4.95. So that's it's 5.0 if we round to one decimal place. Grams. Remember, you're putting your units on absolutely everything. If there's something that doesn't have units, that is supposed to have units, so for example ratio and MR aren't supposed to have units, but if it's supposed to have units, it doesn't have units on, that's the potential of losing marks, and it's really just not worth it. So yeah, there you go. If you've got the same ratio, that's how you do the whole thing. What if you don't have the same ratio? Well, then it's different. And I'm only going to work out the reactants. We won't worry about the products so much, but the reactants. There'll be a few activities for you guys to do so that you can actually give this a go yourself. We will start with H2SO4. H2SO4. Sulfate ion and a hydrogen. So that is sulfuric acid. And we're going to add to sulfuric acid sodium hydroxide. That's going to create water and something else. That's going to create what's it? Sodium sulfate, that's it. Na2SO4. So, Na2SO4. So, sulfuric acid, sodium hydroxide, water, and sodium sulfate. I want you guys to try and balance it. Pause it, give it a go, and then 5, 4, 3, 2, 1, give it a go. And I'm just going to give you the answer because hopefully you already know how to balance. We've got there, so we obviously need 2 sodiums at least. We need, because we've got 2 hydrogens here and 2 hydrogens there, that means we've got 4 hydrogens on this side, 2 hydrogens on that side, multiplied by 2. Now we've got 2 oxygens on that side, 2 oxygens on that side. That should be balanced. So you've got a 1, a 2, a 2, and a 1. So we're going to draw out our little table, and whenever you get a question like this, I really do recommend you draw out a table because it organises everything so much better. And we're going to start with our MR, mass. Let's go with ratio, moles. And we'll start by looking at what's different here. We have got big numbers. Big numbers are really important. So we'll start out with our ratio. Ratio goes here. So we've got no big number here, so that's just another way of saying 1 there. So we're going to have our 1, 2, 2, because there's a 2 there, there's a 2 there, and then there's a 1 there because there's just a imaginary big 1 there. So we've got a ratio, and suddenly it's different. And now we're going to look at what happens there. So we'll start by doing our MR, and if you want to pause and give a go of doing all your MR, give it a go. Remember, the big number doesn't affect the MR, only the small numbers affect the MR. So, give you a go for that. Okay, we'll start with this one. That's 98. Remember, it doesn't have a unit. Alright, so we've had a little go at that. Now we'll look at our sodium hydroxide. That is 40. Water, come on. Start learning some of these off by heart. Some of the more common ones, like sodium, like water, you can just learn to know. And then sodium sulfate is the last one. I'll give you a moment for that. Great, and that is 142. But today we're only focused with the first side. So I'm actually going to say well done if you got those, but we're going to rub this side out, okay? This side isn't important. We'll keep it in the reaction up here, but other than that, it's not important. We're just going to find these, okay? And I'm going to say, let's give you 11 grams there. So we've been given 11 grams of mass, okay? I want you to try and figure out the moles here. And that's as far as I want you to go. I just want you to figure that out. And pause it, give it a go. 5, 4, 3, 2, 1. And that's what we have. We're looking for our moles here. So hopefully you remembered mass, mole, MR. Big triangle. There you go. We're looking for our moles. We cover up our moles. We've got to do our mass divided by our MR. Mass over MR is going to be 11 over 98. And give me that as a decimal because I'm a scientist, I'm not a mathematician. And that is a horrible number, but we're doing it to 2 decimal places. 0.11. Really, on the calculator it says, it actually says 0.1122449. It's a long, horrible number. So just do it to the first 2 decimal places. Okay? And so that is 0.11 moles. And this is where we change, this is where it's different. Okay, this is the most difficult part, is when we do our ratio. So we have a ratio of 1 to 2. And we have our moles of 0.11 to something else, and we don't know what this something else is. So, what do we do to 1 to get it to 2? And it might be, it literally is just simple. 1 to get it to 2. 1 times 2 is equal to 2. And that is the simple bit behind this. You've got to figure out how to get from here to here. So to get from 1 to 2, you times by 2. So to get from 0.11 to the next one, you times by 2, and that gets you to 0.22. So this is actually 0.22 moles. Now, say you had a ratio of 3 to 2. We don't have a ratio of 3 to 2 at the moment, but say if you did. 3 to 2. To get from 3 to 2, you would divide by 3. Divide by 3. 3 divided by 3 is 1. And then 1 times 2 is 2. So you'd go divide by 3 and times by 2. So 0.11 divide by 3 is 0.036 and times by 2, and you get to 0.073. 0.073. So what you're going to do is you're going to divide it until it gets to 1. So divide it by itself and it gets to 1, and then multiply it by whatever it is to get to the second number. So 0.11 divided by 3, and then multiplied by 1. Okay? Multiplied by 2. Okay? And that's how you figure out the ratios. The ratios are simply just a way of saying we have 1 amount of this and 2 lots of this, so we have 2 times the amount of this as we have of this. Remember, moles is just a unit of how many atoms we have. So we have 0.11 times 10 to the 23rd times 6.02. Remember, that's the Avogadro constant. So we have a lot of atoms there, and then here we have 0.22 moles of that, which is double the amount of atoms. So all we're saying is we have 2 lots of these atoms for every one of these atoms. It's just a ratio. And then I'll let you do the very last calculation. 5, 4, 3, 2, and 1. And to get from mass to mole and MR, boom, boom, we need our mass. So we cover up our mass, and you've only got mole and MR left. So mole times MR, because that's what we've got left. So that's 0.22 times 40. And that gets you to 8.8. And there we go, we filled it out. Okay? And if I were you, I'd go do a lot of equations with those, if you can, because it's not an easy concept. Just drawing out that grid and finding what you want. In fact, a lot of the way I like to do it, and if you're doing triple science, which you might be, and it really does help, even if you aren't, listen up anyway, and it does help. But in triple science, you've got a grid. Let's say it's just 2 of them. It's just 2. So we've got sodium hydroxide and hydrochloric acid. You've got lots of different variables. You've got mass, ratio, you've got, what else have you got? You've got concentration, you've got volume, you've got lots of different factors. So what I like to do is I like to say, you could even have, that's moles, that's the last thing. So you could say, I want to find what the mass of hydrochloric acid is. And this is for anyone. I want to find what the mass of hydrochloric acid is. If you have a highlighter, highlight that space. Or just circle it if you don't, although highlighter does help it visually stand out. Just circle it. And that means you're trying to find hydrochloric acid. Okay? And what I even like to do when I'm working out on my whiteboard, which I think is absolutely brilliant because you can rub things out and you can use lots of different placeholders. I say, okay, the first thing I'm going to find is the mass. So I'm going to circle the mass first in different colour. And that means that that's my primary goal. When I've got it, I can rub it out. It's just a great thing to say, okay, I've got that sorted. Okay, just on the home stretch, still higher tier only. The last bit is included on foundation, but still higher tier only. And we've got two things left. First thing, limiting reactants. Limiting reactant is very simple. Say I have sodium hydroxide and hydrochloric acid, and I mix them together. The reactant in excess is the one that I have more of. So I have more sodium hydroxide than hydrochloric acid. So this is in excess. More equals excess. Less equals limiting. And it's limiting because there's not enough of this. This has all been used up. It's been reacted to create your reactor. So there's not enough hydrochloric acid, but there's more sodium hydroxide. So sodium hydroxide and hydrochloric acid, they make, come on, say it with me. I've been saying it throughout the whole time. Water and sodium chloride. Neutralization reaction, right? In the water and sodium chloride, there is going to be some hydrochloric acid still left over. There's going to be some sodium hydroxide left over. There's not going to be any hydrochloric acid because it's been used up. There's no more of it. There is lots of this left. And that means that if it's a solid, it can form something called a precipitate. Which is a solid that is suspended in a liquid, and we could have some sodium hydroxide, and there's still sodium hydroxide left in the beaker. So we take our beaker, our conical flask. That is a horrible conical flask. I'm going to draw that again. Conical flask. There you go. And we put in our hydrochloric acid, we put in our sodium gets reacted, and all of a sudden we have water and sodium chloride. But we still might have in there some of that sodium hydroxide because it's not been reacted. Okay? It's less economical to have a limiting reactant, for example, so it costs more. You need a lot more funds to have a limiting reactant. It also might mean that you have less product than expected. So you want a certain amount of product. So you buy lots of this, but not so much of this. And that means that you can't create enough product because it's in a 1-to-1 ratio. However much of this, you need however much of this. If I have 8 grams of this, I need 8 grams of this to create the products. Otherwise, you're never going to create any products. Sometimes you may even be asked, what is a limiting reactant? What is the limiting reactant? And you may have to point it out. And that is relatively easy. The very last thing is concentration. Concentration is mass over volume. Mass over volume. And this is simply grams over decimeter cubed. So we have our little triangle. Alright, so you guys have made it this far. This is the very, very last bit. This is on moles. So very, very last bit in this topic. So made it this far. This bit is also on the foundation paper as well as the higher paper. And it is concentration. Concentration. I'm going to use blue because my black pen is running out. So what is concentration? And we can think of lots of different definitions of the word. Concentration in a more literal sense, or sorry, in a more English based sense, could be you're actually concentrating on something. You're trying really hard to devote all of your attention to it. So that's one definition of concentration. But the definition of concentration that we're looking at here is how much of something do we have in a given space, okay? So if I take blue and red, and I'm literally just going to do dots, okay? The red dots, and there's lots and lots and lots of red dots, that is water, right? And then I'm going to put in blue dots. 5, 6, 7, 8. There we go. I've got blue dots, and my blue dots are going to represent sodium chloride. Can everyone see that well? Okay. Concentration is how many blue dots I've got compared to how many red dots I've got. Okay. And so I can do that by adding up all the blue dots and comparing that with all of the red dots, okay? But another way, and the way we'll be asked in the exams, is we're going to be given a space. So let's say a square, and then we've got dots inside of it, or let's say, yeah, little dots inside of it. 1, 2, 3, 4, 5, 6, 7, 8. And we're asked the concentration of this. Now this is, let's say this is 3D, and let's say that this is 1 litre, so it's 1 decimeter cubed. 1 decimeter cubed equals 1 litre. But yeah, 1 decimeter cubed, or 1,000 centimeters cubed. That's the same thing. 1 decimeter cubed is 1,000 centimeters cubed. And that's how big, that's the volume of this box. And we're asked to find the concentration. Well, we can divide the number of atoms divided by, hold on, let me get out my green so we've got something different, our volume. And that's concentration. And we get out the unit of atoms per decimeter cubed. So, let's say that we have 1 decimeter cubed here, and we have this many atoms. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 sodium chloride ions. Sodium chloride atoms, sorry. So we've got 8 per 1 decimeter cubed. So we do 8. We do 8, and we do that divided by our 1, and that is equal to 8 atoms per decimeter cubed. Can we agree that that's 8 atoms over decimeter cubed? So if we just ignore the numbers at the moment, we've got atoms divided by decimeter cubed, and over here we've also got atoms divided by decimeter cubed, and that's where the units come from. But we also have to remember, sorry. Now, another way of thinking about this is by thinking about it in terms of grams. So grams is just another way of saying how much we have of something. So instead of doing atoms over volume, we do mass over volume. So we're going to do mass divided by our volume. That equals concentration, our big important word at the top. But we measure mass in grams and volume in, come on, it's always decimeter cubed. It could be centimeters cubed in the question. Yes, it might ask you in the question with centimeters cubed, but the standard is decimeters cubed, okay? So decimeters cubed. And that means the concentration is measured in grams per decimeter cubed, or in other words, grams per decimeter cubed. It doesn't matter which way we write it. Actually, it will in the exam, but this is just another way of saying it, right? Grams per decimeter cubed, grams over decimeter cubed, so grams divided by decimeter cubed gets to this unit, and that's the unit of concentration there. So, say we have 12 grams of sodium chloride, and we divide that by our 1 decimeter cubed. We get out, what's it? What is it? It's 12 grams per decimeter cubed. And that's one way of working this out. It's how much of mass do we have in a given space, and that's concentration. And there's a triangle for that. So if there's people there who absolutely love their formula triangles, I've never been a fan of them, but I know a lot of people like them. So if you like formula triangles, this will be useful for you. But we have our triangle. We've got our concentration. I'm just going to put const. Don't do that in your exam. Always write out the full word, concentration. We're going to have our volume at the top. And we're going to have our mass here. So, if the question says we have, let's say, sodium chloride. We have 15 grams and we have 7.5 decimeter cubed. Find the concentration. Okay? And pause that and give it a go. 5, 4, 3, 2, 1. Brilliant. Well, we've got mass, grams is mass, and we've got, oh, that should be a cubed on the end. And we've got volume, here, decimeter cubed. So we're looking for concentration. So we cover up concentration, and we see we've got volume and mass. We do volume divided by mass, and that means we've got our 7.5 over 15, and you can put that into your calculator, but that's equal to, another way you can look at that is it's 15 over 30, and that's 0.5, or you can just know that 7.5 is half of 15. So there we go, we've got 0.5, but are we finished? No, we've got to remember our unit. Our unit is grams per decimeter cubed. We found the concentration, we've got a unit, and hopefully that's 3 marks. Remember, if you've got conversion, that could even easily be another mark on top. Say if it had 75 centimeter cubed, we know that 1 decimeter cubed is 1,000 centimeters cubed, so we do 75 divided by 1,000, and that gets you to decimeters cubed. So that could be easily another mark on top. And that there should be all of moles. Go have a look, do some practice questions, and if you've got any issues, mention them in the comment section. Thank you.